Mhm.
Okay, great.
Can you see my slides now?
Okay, so let me introduce. Yeah, great. Thank you. All right. So let's start. Today we are very happy. It's a great honor to have Zohar Komargodski from Simon Center for Geometry and Physics, SCGP. And his topic today will be the high temperature limit of quantum field theory. And as Zohar mentioned, that he'll be given even more advanced version compared to the version he gave maybe 1 or 2 weeks ago.
2 weeks
so
ago.
we should a few weeks ago, yeah. So we'll be very happy to hear more. Okay, so let's welcome Zohar.
Thank you so much. Maybe I should say that if you guys or like to unmute yourself and ask any question during the talk, please do so. I'll be happy if you just interrupt because I'm not able to follow the chat anyway. So just interrupt me whenever there is any question. So this is some work that's based on something that we're writing up that will maybe appear this or next week. I mean, will be submitted this or next week. It's with Chang-Ha Choi, who is my student at Stony Brook. And it's with the Hebrew University group of Noam Chai, Soumya-Deep Chowdhury, Eliezer Rabinovici, and Michal Smolkin. Let me introduce the topic. So the motivation is that, as you all know, there are many interesting Hamiltonians. I mean, I'm talking about quantum systems here. So there are many interesting Hamiltonians that exhibit symmetry breaking at 0 temperature. So we know of many such examples, both from condensed matter statistical physics and particle physics. So let me just mention a few of the most familiar examples. So one example is ferromagnets, quantum ferromagnets, which lead to ordering and ferromagnetism at low temperatures. Massless QCD is probably the most famous example in particle physics, since it exhibits chiral symmetry breaking at 0 temperature. The Néel phase in quantum antiferromagnets is a famous example, and so on. Now, usually the intuition is that when we study these quantum systems at the finite temperature, then these symmetries are eventually restored. If we raise the temperature sufficiently, these symmetries are all supposed to be restored. So of course, intuitively, if you have a magnet, you heat it up, then you expect that magnetism would be lost. If you look at the literature in the condensed matter and material science, all the phase diagrams that, as far as I know, were ever discovered, indeed are consistent with symmetry restoration at very high temperature. So this, let me just explain this diagram because this will be somewhat important for the motivation. I just stole this diagram from a paper by Bitko and the collaborators. So the y equals 0, the x-axis, so y equals 0 is just some parameter in the Hamiltonian, which in this case is some transverse magnetic field. And at 0 temperature, there is a phase transition, which is a standard 0 temperature phenomenon, that there is a critical point phase transition at some particular value of the external parameter. And then on one side, there is a ferromagnetic phase where some symmetry is broken. And on the other side, there is a disordered, trivial paramagnetic phase. And the thing that you would always find in the literature is that the phase transition line, which here is this black line that I'm following with my mouse, this particular line goes to the left. So if you start from the critical point, it goes towards the ferromagnetic phase. So it caps off the ferromagnetic phase. And then at high temperatures, the symmetries are restored, while at low temperatures, the symmetries are broken. So if this black line went the other way, it would be quite bizarre. So we can ask, why is it always like that? And there are basically two arguments. One is a very lowbrow argument from high school. And the argument is that at very high temperatures, what dominates the free energy is the second term, ST, where S is the entropy. And high entropy states, so at very high temperatures, what dominates are high entropy states. And high entropy states tend to be disordered. That's what we're learning in high school. A much more sophisticated reason comes from the ADS-CFT correspondence. In the ADS-CFT correspondence, like 10 years ago, there was a huge activity in which the finite temperature phases of various condensed matter-like systems were linked to black holes. And they essentially proved the no-go theorem, which is that black holes, which are uncharged, namely there is no chemical potential, just this thermal ensemble, no chemical potentials, do not have hair. And the question of hair in the ADS-CFT correspondence, the no hair theorem, is basically dual to this statement that I'm making about conformal field theories. So actually that's the reason that we originally got interested in this problem. I got interested in this problem for this reason, that I was trying to prove the no hair theorem. So the no hair theorem in ADS is translated in CFT to the statement that symmetries are restored at high temperatures. Okay. And there is a sort of a proof in gravity, but it would be interesting to know if there is a statement of that sort about conformal field theories. So the question is very clear. I think it's well defined, non-perturbatively. We study a conformal field theory in d+1 space-time dimensions. We turn on some temperature T. And of course, when you're at the critical point, those of you who are in condensed matter know this very well. It doesn't matter what temperature you are in. If you're at the critical point and you just raise the temperature, it doesn't matter what's the value of the temperature, since this is the only scale in the problem anyway. So the question is, given a conformal field theory at temperature T, can symmetry breaking take place? The question is phrased about conformal field theories because if the answer to this question is negative, namely that there is, if the answer to the question is that there could be symmetry breaking at finite temperature, that would mean that there are materials or phase diagrams where the line bends the other direction, so to speak. So it's the ordered phase that exists up to asymptotically high temperatures, not the disordered phase. And that's quite bizarre. And as I said, this is dual to the no hair theorem, but it's still interesting to ponder on the question of whether it's actually true in all unitary conformal field theories that at high enough temperature, that at non-zero temperature, they never break any symmetry. Now let me make a small remark because there are many experts on that in the audience.
Excuse me, I have a question.
Yes, hello.
So clearly in the crystal, we could have a critical point, but the crystal always break translation symmetry. So, so whether conformal field theory or conformal theory can never break symmetry, whether there's some conditional qualifier.
Right, so you could consider many variations of this question, but the variation that I'm interested in is you start from a conformal field theory in d+1 dimensions, which is completely Poincare invariant, and you turn on temperature in that theory. I will not have a lattice or a crystal. It will be just a continuum conformal field theory at finite temperature. Okay, and you can ask then whether this conformal field theory at finite temperature breaks or does not break a symmetry. I will go over some examples, and I believe you will agree that there are no examples where the conformal field theory does break a symmetry at finite temperature, at least not in the literature.
But you assume conformal field theory do not break any symmetry at 0 temperature. That's a starting point.
So the starting point is a 0 temperature conformal field theory, which is completely conformal invariant. So it's invariant under the Poincare symmetries. It's invariant under the conformal symmetries. And furthermore, it has a unique gapless vacuum.
Okay.
That's the starting point, a unique Poincare invariant, conformally invariant gapless vacuum in infinite volume. And then you heat it up. That's the starting point.
Okay, thank you.
So you could think about the free fermion. The free fermion is the simplest example. A free relativistic fermion. We know that once you heat it up, the fermion gets a mass. And of course, there is no symmetry breaking in that case.
Zohar, can I ask a question?
Hi, yes.
Yeah, hi. So are you assuming anything about what symmetry this CFT has? Does it have only ordinary symmetries? Does it have higher form symmetries?
Right. So, okay, I'm going to talk a little bit about that. This talk is only about, magnetic like magnets. Basically, I'm only talking about on-site. I'm not even going to talk about anomalies. It's not going to be important. So think about on-site ordinary global symmetries. Now, this kind of question that I'm asking for generalized symmetries, the answer is, of course, the opposite, because the confinement typically takes place at non-zero temperature.
Mm-hmm.
So higher form symmetries behave differently. And that's another reason that I get interested in the problem. I wanted to understand why higher form symmetries behave oppositely to ordinary symmetries. But even for ordinary symmetries, I argue that the answer is not really known. So I want to, in this talk, I'll only discuss magnetic-like symmetries, ordinary on-site symmetries of magnets. But I'm talking about CFTs, not about lattice models. Talking about CFTs, which have ordinary unitary global symmetries, and I'm asking what happens at finite temperature.
Great, thank you.
Probably the most familiar example is the ON model that I'll review a little bit, which has a ferromagnetic and paramagnetic phase. And when you heat it up, the ferromagnetic phase is capped off, and the high temperature phase is paramagnetic. Okay, so
Zohar?
yes.
I have also a question. So in this proposed phase diagram, so this is perhaps the goal of your talk. Is that right? We want to obtain this.
Well, I'm just asking a question. This talk is about this question of whether we actually know whether the high temperatures restore the symmetries or not.
Mm-hmm. But I'll go to that phase diagram. I was wondering, say, whether you will also be interested in examples such that perhaps there is no odor at zero temperature, but at finite temperature it become odor.
Well, I'm only talking about ordinary symmetry.
Sorry, and
yes,
at a further higher temperature, the odor can disappear. I think these are some phenomena called reentrance that happens in.
I'll talk about this reentrance in a few slides, but let me just emphasize why this is not going to be an issue. So to simplify the question and to also make contact with the no-Hare theorem and ferromagnets, I'm talking about CFTs. And for conformal filters, any temperature is the same as any other. So once you know the answer at some temperature, you know the answer for any temperature. So this phenomenon that at some temperature you get one answer, at another temperature you get another answer, that's not going to be possible now. Okay, so to simplify the problem maximally, I'm talking about CFTs, which at zero temperature are gapless and conformally invariant. And then you turn on some temperature, doesn't matter which. Okay, you're talking about systems with many scales where there are several layers of dynamics. I'll actually mention that in a second, and then tell me if that answered the question. So indeed, in '74, Weinberg constructed the field theory that is supposed to be like a mock field theory for some kind of a SPT material. I mean, not SPT in the modern sense. This sodium potassium tetride material. And this material is famous. You can even buy it on Amazon. It's called the Rochelle salt, because between the temperatures of 18 and 24 Celsius, minus 18 and 24 Celsius, it has a higher crystal symmetry than at lower temperatures, which is quite bizarre. It's not a standard crystal. Usually crystals don't behave that way. They have the maximal symmetry at low temperatures, and then they become liquids or something. But this crystal has like what you meant. They call it non-restoration, symmetry non-restoration. That you heat it up, and instead of melting, the crystal becomes even more ordered. But of course, eventually, when you heat this crystal up sufficiently, it becomes completely disordered. But there is still some phase, which is an intermediate phase, which is very interesting, which exhibits more ordering than the true low temperature phase. And Stephen Weinberg constructed in '74 a field theory that has similar properties, which has several scales. And I'm not going to talk about it. This is very interesting, but if you want to make contact with this idealized question that I'm posing, you have to think about the critical points at finite temperature. That's also the natural setup for the ADS-CFT correspondence. So I'm not going to try to explore this phenomenon. Okay, so is that what you asked about, the non-reentrance? Does that address your question or not at all?
I think your CFT assumption probably already.
Yes, yes.
Not, yeah, no, it's fine. Thanks.
I'm just trying to make like, you know, to try to make the question super concrete, to make a few assumptions that make the question super constrained and concrete. And if we can try to solve that question, that would already be more or less satisfactory.
Yeah. Thank you.
Can I just ask, hi Zohar.
Yeah.
So in these reentrant systems, I can kind of think about it as like maybe there's a critical point at some temperature, but there's also some gap degrees of freedom that don't participate in the CFT, and then maybe at some higher temperature, those lower in energy and are responsible for a reentrant phase.
Oh yeah, that's exactly what you should think about, right? If you look at Weinberg's model, it has 2 scales, and there is some high temperature scale, and the high temperature scale presumably has new degrees of freedom, which would cause a reentrance.
Thanks.
That's exactly right, yes. Yeah, but I'm just saying that since I don't believe that the answer about high temperature limit of QFT is generally known, it's very natural to focus the question on conformal filters, because the high temperature limit is a conformal filter very naturally. So of course, lattice systems are different. The high temperature limit of lattice systems is much simpler, but the high temperature limit of quantum filters essentially boils down to the question of the high temperature, about the high temperature limit of conformal filters. So it's a natural restriction. So the question is, are there unitary, local, non-trivial theories which break a global symmetry at finite temperature? Okay, ordinary global symmetry. So let me tell you what I'm gonna do here. So what I'm gonna do here is that I'll actually construct a class of interesting examples in 4 minus epsilon dimensions, which do break a global symmetry at finite temperature. So I'll construct conformal filters in 4 minus epsilon dimensions that do break a global symmetry. The examples that I'll construct, most of them do not carry over to an actual integer number of space-time dimensions. They do not carry over to 2 plus 1 space-time dimensions. But at the very end of this talk, I will present a model that seems to work even in 2 plus 1 dimensions, not just in the epsilon expansion. So here I'm just saying that I'm just drawing again the typical phase diagram that you encounter in the literature. And I mean, asking if this is really a must. Now, let me just quote 2 theorems that are very basic in this subject that you must remember. In 1 plus 1 dimensional systems, you cannot have finite temperature symmetry breaking. That's obvious from modular invariance, for instance, or from the fact that the finite temperature in 1 plus 1 dimensions is a little bit like quantum mechanics, and there is no symmetry breaking in quantum mechanics. Similarly, in 2 plus 1 dimensions, you cannot have continuous symmetry breaking in 2 plus 1 dimensions. You can only have discrete symmetry breaking in finite temperature. So what did I must have said something wrong. In 2 plus 1 dimensions at finite temperature, you cannot have continuous symmetry breaking, but you can have discrete symmetry breaking. So the reason that some of these examples that we've got do not carry over straightforwardly to epsilon equals 1 is because they involve continuous symmetry breaking at finite temperature. So there is some non-perturbative infrared effects that remove this phenomenon in 2 plus 1, strictly speaking. But we also have a version of the same thing that involves only discrete symmetry. And then it seems to work. Okay, so basically this is the Mermin-Wagner-Coleman theorem. It's a version of the same thing, only at finite temperatures. And this I don't even know who should be credited for that. Maybe Landau? Okay. So before I jump in, I just wanted to make a few pedagogical comments. These are not about conformal filters at finite temperature. These are just some pedagogical comments about finite temperature field theory. And this is very familiar to probably all of you. But the main point here is that even if you take a model that at 0 temperature is very well understood, and it's in fact free. So here I'm talking about the mean field theory of 5 to the 4 in 3 plus 1 dimensions. So this flows the long distances to mean field theory, and it's a very easily solvable model at long distances in 3 plus 1 dimensions. But even if it's very easy at 0 temperature, it may not be so easy at finite temperature, because once you reduce the model on a circle, there is a zero mode on the circle, which I call phi naught. And this zero mode doesn't have a mass because it's a zero mode. And in 2+1 dimensions, a quartic interaction, unlike in 3+1 dimensions, where it goes to mean field theory, a quartic interaction in 2+1 dimensions is strongly coupled. So potentially, even a model that's very easy at zero temperature can become strongly interacting at finite temperature. So really, to understand whether the zero mode is strongly interacting or not, you have to try to compute some diagrams. And these diagrams basically represent the quantum induced mass for the zero mode from loops of the Matsubara modes. And you have some strong coupling scale in the problem, which is the scale where the quartic interaction for the zero mode becomes strong. And you must be careful to make sure that the mass that is induced by integrating out the higher Matsubara modes is above that strong coupling scale. Otherwise, you don't know what you're doing. And this is the famous infrared issue in thermal field theory. And in this example, one is very lucky. One proceeds with the computation of the thermal mass. One finds that it's actually positive. So there is no symmetry breaking at finite temperature. And the scale of the thermal mass is lambda, which is the coupling, times temperature squared. However, the strong coupling scale is lambda times the temperature. So one is very, very lucky in this example, because the thermal mass is just a square root of lambda above the strong coupling scale. So you're saved from catastrophic infrared dynamics by the square root of lambda factor, and you can reliably conclude within this framework of perturbative quantum field theory at finite temperature that the Z2 symmetry of this phi to the 4 model is unbroken. And so this basically boils down to computing the thermal mass. That's all there is to it. And that's a simple example that shows that there is no symmetry breaking at finite temperature. In this trivial example. But anyway, the issue here is that there is this infrared issue, the infrared potential non-perturbative dynamics at non-zero temperature, and one should be careful about it. So I'm not going to keep mentioning it in every example that I go over, but in every example that I go over, one has to check that this is correct, that you're saved from these catastrophic non-perturbative questions. Okay, so here I'm again listing some possible models you could study, but in this talk, I'll only talk about the epsilon expansion and some continuation beyond, like truly 2+1 dimensional models. Okay, so the epsilon expansion is of course just a machine that generates many interesting conformal field theories. And this is a very natural class to try to study with our tools and try to ask this question about symmetry breaking in conformal field theory. So the models are just parameterized by all the possible couplings of 4 scalar fields with arbitrary indices ij, kl. And we're going to assume that epsilon is the smallest parameter. If you assume that epsilon is the smallest parameter, then just Wilson-Fisher, yes?
So this lambda ijkl should be permuting symmetric and specify just ijkl be the same parameters.
Yes.
JK, okay, sure.
Yeah, lambda twiddle is a fully symmetric tensor with 4 indices. So the fixed points in the epsilon expansion are fixed by this, equation of Wilson and Fisher, essentially. That's how you look for fixed points at very small epsilon. You need to solve this algebraic equation for such symmetric tensors with 4 indices, as Jovan said. And it's to write this equation in a mathematically natural language, it's very convenient to get rid of the 16 pi squared and epsilon. So you just rescale the coupling in this fashion, and you get a beautiful real algebraic equation. And solutions of this equation basically correspond to fixed points. And many of these fixed points in the epsilon expansion, as you all know, correspond to interesting fixed points, even in 2+1 dimensions, which is epsilon equals 1. Of course, the extrapolation is often problematic, but in many cases it works very well. So you have to deal with these algebraic equations to try to classify fixed points in the epsilon expansion. Now you can ask, what do we know about finite temperature? Well, it's very easy. If you give me a solution of this equation, I can compute the thermal masses simply by tracing over two indices. And because this tensor is fully symmetric, it doesn't matter which two indices you trace over. So there are some prefactors that have to do with this Casimir energy. You basically encounter the same type of diagrams as this one, and there is this infinite sum that appears also in many places. So the 24 is from this infinite sum over the integers. And so you get essentially that. That's the final answer for the thermal masses. And then the question is whether they're positive or negative. Now, using the fixed point equations, you can simplify the trace over the couplings. And that's the final answer for the mass squared of these systems. So there is a piece that's manifestly positive definite. The second term is manifestly positive definite. And the first term is not manifestly positive definite. So one doesn't lose hope, right? You write down these equations, you compute the thermal mass, and you find the piece that's not manifestly positive definite. So there is some hope that maybe we will find examples, interesting examples. Yet there is a second, the second piece here is positive definite. So it's not obvious that you will find examples. So how do we attack this problem of finding fixed points that are interesting? Actually, a very useful way to attack these equations is by symmetry. So the maximal possible symmetry that such a tensor can preserve is On, because there are n fields pi I, where I goes from 1 to n. And there is essentially a unique choice that preserves the full On symmetry. This is the choice. This is the On model. So it's a fixed, this tensor is fixed up to one coefficient. You plug this into this equation, you find the coefficient. And this is just the famous On invariant fixed point. And then you compute the trace, you find the thermal masses. And of course, the thermal masses are all positive. So they're given by this n plus 2 over n plus 8. And many people even remember it by heart. This is in many, many books. So there is no symmetry breaking in the On model. And there is the bi-screening and a standard thermal gap. Actually, you can generalize this result to a huge class of theories in the following way. So you have to look for fixed points that preserve a slightly smaller symmetry than On, right? So there is a general theorem that we proved. We call it a no-go theorem. So what's the no-go theorem? If the fixed point preserves any group G, which is a subgroup of On, such that the fundamental representation of On is irreducible as a representation of G, then you only get the positive thermal masses. This condition of irreducibility of the fundamental representation is equivalent to requiring that there is one quadratic invariant of G. Okay, so every fixed point for which the fundamental representation of On is irreducible will not work. Namely, it will not generate symmetry breaking at finite temperature. And this more or less explains a posteriori why many familiar quantum magnets don't break a symmetry at finite temperature. Because actually this class of models with a single quadratic invariant cover a huge number of models that many of you know. The On models, cubic models, tetrahedral, bifundamental, something that's called the MN models, Michel fixed points, tetragonal fixed points. And there is even a recent review of all these classes by the Bootstrap collaboration. So there is a simple no-go theorem that I'm not going to prove that covers basically all the models that you guys know. This is what group theoretically, this is what you need, that the fundamental representation of On is irreducible. Okay, are there any questions about this statement? Okay, so this covers more or less all the fixed points you would try. But there is one class of fixed points which have many interesting properties that I'm going to explain that are not covered by this no-go theorem. Sometimes this class of fixed points are called biconical fixed points. There are many papers about these fixed points, for instance, by Calabrese and others. These fixed points have a symmetry group that's like that, On times On minus M. And the fundamental representation is clearly reducible. So they do not follow the no-go theorem. They may not be subject to the same conclusion. So let me just explain what these models are, and then I'll explain some very surprising properties of these models. So first of all, these models have three quartic possible QWERTY couplings that you should consider within the epsilon expansion. They're alpha, beta, and gamma. And you can easily write down the beta functions. Okay, this is just a list of beta functions. We cannot solve these beta functions explicitly. They are, complicated algebraic equations. But I'll tell you many properties of the solutions. So the first case you want to consider is maybe equal rank, where m and n minus m are the same. So you're talking about OM times OM symmetry. Actually, the equal rank case is easily solvable. So these equations become easily solvable, and one finds this fixed point. Of course, one also finds the full ON invariant fixed point, where alpha, beta, and gamma are all the same. But this is not an interesting fixed point since it obeys the previous no-go theorem. But one finds also a new fixed point, where gamma is potentially negative. If m is bigger than 4, so one of the groups has a rank bigger than 4, then the coupling gamma, which is this coupling, could be negative. However, you can then compute the masses, thermal masses in this model, and again, they are positive. So there is no symmetry breaking again. So the equal rank model, again, doesn't work, even though it doesn't obey the no-go theorem, at least not naively. So there are only bad news so far. We don't find anything interesting. But then you go to the non-equal rank case. So you study the biconical models, where m and n minus m are not the same. And then you encounter many surprises. So it's actually useful to start from a large n limit. So you take n to be very large, you take m over n to be fixed, and you rescale the couplings so that there is a smooth large n limit. What you find are several very surprising facts. These are facts about the large n limit of these biconical fixed points. The first fact about the large n limit of these biconical fixed points is that there is actually a circle of fixed points, not a unique fixed point, but there is a circle of fixed points. And this is true for any x. I remind you that x is m over n. So for any x that is fixed in the large n limit, instead of one fixed point, you find a whole circle of fixed points. Now, of course, this circle is not going to survive to finite n, but at the large n limit, there is a circle. And many points on the circle are going to survive to finite n. For instance, this red star is the familiar critical ON model. These blue points are some decoupled critical and free bosons. So they are going to survive. And there may be other points on the circle that would survive. So fact number one is that there is an exactly marginal operator at very large n. This is surprising because we're in 2 + 1 dimensions and there is no supersymmetry. And usually there are no exactly marginal operators in 2 + 1 dimensions. But here there is in the large n limit. That's point number one. Point number two, which is even more bizarre, is that if you are on this on the half a circle that is at gamma negative, so if you're on this part of the conformal manifold where gamma is negative, not only that there is an exactly marginal operator, there is also a moduli space of degenerate vacua, exactly degenerate vacua. That's also not something that you expect in quantum field theory in 2 + 1 dimensions without supersymmetry, but there is a moduli space of vacua because the potential can be written as a full square. So if phi1 squared is the same as phi2 squared with this ratio, then the vacua are all degenerate. And that's exact at large n. So at large n, we have both an exactly marginal operator and the moduli space of vacua. You can depict this moduli space of vacua like that. So at the origin, there is, of course, a critical point at 0 temperature. And away from the origin, at 0 temperature, you have Nambu-Goldstone bosons and a dilaton particle, massless, which is a massless Nambu-Goldstone boson for conformal symmetry breaking. So the 0 temperature behavior of these biconical fixed points at large n is quite curious. At large n, they have a moduli space of vacua and a moduli space of conformal field theories.
Zohar,
Yes.
Can I make a naive suggestion?
Sure.
Is it possible to use a full screen?
Oh, I didn't.
What I mean is that
I didn't.
Yeah, the scrolling will be.
How is it now?
That's much better. Yes, I'm sure that some audience also will feel that way. Yeah, this is.
I didn't realize that full screen. Sorry. Yes.
Thank you.
Okay, so these fixed points have these curious properties. And then we computed the finite temperature. What happens at finite temperature with the ground states of this theory? And you find something, again, surprising, which is that, of course, physical intuition would suggest that if there is a continuum, if there is a continuum of vacua at 0 temperature, they would be lifted at finite temperature. But instead, they are deformed to a hyperbola. So there are 2 possible hyperbolas. One is when the hyperbola crosses phi 2, and one where the hyperbola crosses phi 1. They are not the same because they correspond to different symmetry breaking patterns. And that depends on the sign of this coefficient C in the equation for the hyperbola. And one should compute it, but of course we computed it and we know the answer. I'll summarize it soon. So in fact, the moduli space of vacua is not lifted, even at finite temperature, but instead you find a hyperbola that no longer crosses the origin. And you see that physically that's enough to conclude that there is symmetry breaking at finite temperature, because now there will be some finite rank corrections, but the ground states never cross the origin anyway. So it is impossible that the true vacuum of the fully corrected theory would be at the origin, because there is a hyperbola at large n, and the hyperbola does not cross the origin. So small corrections cannot bring you to the origin, and there will be a vacuum somewhere on this hyperbola. A very interesting fact is how does this correspond to the equal rank case? I told you that for the equal rank case, the thermal masses were positive and the true vacuum was at the origin. So it turns out that for the equal rank case, the hyperbola degenerates. So C equals to 0. And it's only for the equal rank case. For the equal rank case, the hyperbola is degenerate. It crosses the origin. And that's why it's potentially possible that the origin is the only true vacuum at finite temperature. But as soon as you go to non-equal rank, it's impossible anymore. So at non-equal rank, symmetry breaking is guaranteed, at least for a large enough finite rank at finite temperature. So we computed the sign of this coefficient C, which tells you which hyperbola you get. And let me just summarize. This is irrelevant. I'll just summarize what you get. So what you get, oh, one more thing. So if you know which hyperbola you get, it is still interesting to ask where is actually the vacuum once you include finite rank corrections and so on. And the answer turns out that it's always at the vertex of the hyperbola. So the vertex is where the hyperbola intersects one of the axes. Physically, what that means is that either phi 1 condenses or phi 2 condenses, but not both. So that means that either the OM symmetry is broken or ON minus M symmetry is broken, but not both. That's what you find when you compute 1/n corrections to these biconical fixed points.
Excuse me. Left figure you just shows different sign of a C, right? C larger than 0, C smaller than 0.
Yes.
Yeah, just double check. Thanks.
Right. So you have to compute the sign of C. That's the only computation you gotta do. And then you have to understand that the true vacuum is the vertex of the hyperbola. So the large n limit, you can solve the large n limit, and you can do it even at finite epsilon. You don't have to do it at small epsilon. So, and then the only non-trivial computation is the sign of the hyperbola and where the vacuum actually lies on the hyperbola. You have to understand which hyperbola you get, and then where is the vacuum of this hyperbola? The true vacuum at finite n. So this is quite a bit of work, and you can do it at any epsilon. And the answer is very simple. So it's much easier to summarize the answer than go over the idea, then go over the computation. The answer is that you take the group OM times ON minus M. You check which is the smaller group. So which is smaller, M or N minus M. And the smaller group is broken. And that's it. If they're equal, which is the equal rank case, then none of them is broken. And that's the final conclusion, all right? So in these biconical models, we constructed fixed points which look unitary, they look healthy, the potential is bounded, and the group which has the smaller rank is the one that's broken. If they're equal, none is broken. So this leads to some manifold of Nambu-Goldstone bosons, right? So for X is the ratio of the ranks. So at X equals 1/2, which is the equal rank case, we have a thermal gap. There is no symmetry breaking. But at any other X, which corresponds to the non-equal rank case, there is symmetry breaking of this form. So you get a sphere of Nambu-Goldstone bosons. And you get a Nambu-Goldstone bosons which parameterize a sphere. So that's the answer in the epsilon expansion as well as beyond. This is the answer at finite epsilon, which is smaller than 1. So we have examples of fixed points which look like some finite quantum magnets that do break a symmetry at finite temperature, critical points that break a symmetry at finite temperature. But as I already anticipated, these examples are not going to work strictly in 2+1 dimensions because there are infrared non-perturbative effects due to Coleman-Marmin so they call it in conductor matter, I think, the Mermin-Wagner-Coleman theorem, which lift this degenerate Nambu-Goldstone bosons. So this works everywhere outside of 2+1 dimensions, essentially. So this is the conclusion for now. We have a construction of expansions, and yeah, and they don't work in 2+1 dimensions. Yes?
Yeah, previous slide. Sorry, I must miss something. So what's the this quotient space this as a sphere when x is fractional? I'm
no,
not
and
sure the
x is the rank of the smaller group, so it's m, and x is m.
Oh, okay.
So it's a sphere of dimension m-1, where m is small. If m is smaller than n-m, then it's a sphere of dimension m-1.
What's the value of x running from?
Here, x goes from 0 to a half. You can pretend that x is a continuous parameter. It's just n over m. But of course, m over n, sorry. So m over n is some fractional number. So you can pretend that x is almost continuous at large n. But of course, physical models correspond to situations where x is a rational number, m over n, and then n over x is the integer.
Okay. All right, no problem.
Okay, now let me make some comments about 2+1. So we have this symmetry breaking pattern at finite temperature. Right? That's what we found so far. This symmetry breaking pattern cannot take place for generic M in 2+1 dimensions because of Coleman's theorem. But it's still very interesting because the mechanism that leaves the Nambu-Goldstone bosons is deeply non-perturbative and it's infrared. And it leads to a tiny, tiny mass for these Nambu-Goldstone bosons. It's exponentially small in n, where n is large. So this is still a very interesting thing in the context of statistical physics, because it's a very violent violation of the idea that the gap should be of the order of the temperature. Here, the gap is exponentially smaller than the temperature, because the mechanism that leaves the Nambu-Goldstone bosons is deep infrared, is deep in the infrared, and it's tiny. So there is no symmetry breaking in this model, strictly speaking, but there is a huge violation of the idea that the correlation length should be of the order of the inverse temperature. So this still behaves counterintuitively, but it's not, strictly speaking, a counterexample to the idea that symmetries are restored at finite temperature. Are there any questions? Now, I'm planning to go over some special case which is interesting in truly 2+1 dimensions.
Sorry, maybe I could ask you a question. So I guess what I learned is that at any finite temperature, there is a non-trivial vacuum, which is a symmetry broken.
Yes.
But at 0 temperature, there's no problem because you have this degenerate vacuum. So therefore,
no, at 0 temperature, you have a unique massless vacuum, gapless vacuum. It's just a conformal filter at 0 temperature.
Right, but at any finite n, this manifold of vacua is going to be disrupted, right? It's not going to be degenerate anymore.
Right. So again, so this is the manifold of vacua at very large n. It's this blue line.
Yes.
At any finite n, the only point that remains is at the origin.
Which is gapless.
And it's a gapless conformal filter.
Right. So how do you think that your finite n finite temperature, large n finite temperature result would extrapolate to 0 temperature?
Okay, so At zero, let me just say again, it's a very good question. So it's zero temperature. At large n, we have a manifold of vacua, and at finite n, it's lifted, and we have only one vacuum at the origin, which is a conformal filter, just a gapless vacuum, a gapless unique vacuum. At finite temperature, we have a manifold of vacua that looks like a hyperbola. And when we take into account finite rank corrections, it's again lifted, as you say. And the only vacuum that remains is here at the vertex of the hyperbola, okay? It's at this intersection of the hyperbola with one of the axes. As you change the temperature, the hyperbola goes towards the origin because you see the focus of the curvature of the hyperbola is fixed by the temperature squared. Beta is the inverse temperature. So when you put temperature equals 0, which corresponds to beta equals infinity, the hyperbola disappears and it becomes a straight line. So essentially, the order parameter for symmetry breaking goes like temperature squared. That's the easiest way to say it.
Okay.
The value of the condensate that breaks the symmetry at finite temperature is proportional to temperature.
Right.
Is that clear?
Yes, but except that this doesn't fit to the general condensed matter type of phase diagrams.
Well, that's why I'm giving this talk, because it's a weird thing. I understand that this is very atypical, and I also said that there is a no-go theorem that covers many of the familiar cases. But we did find examples that behave counterintuitively. So you see, I wrote it here that the condensate goes like the temperature squared. So when you remove it's actually very strange, because when you learn about symmetry breaking in books, they say that low energy states could be in two sectors, two superselection sectors, and when you go to high energy states, there is a unique continuum. But here it's the opposite. It turns out to be the opposite. At low temperatures, there is a unique vacuum, and at finite temperatures, it seems that it's split. And I don't understand exactly how that can be, but yeah, that's what's happening. So somehow finite energy density states are split in finite volume to two superselection sectors, and not the low energy density states, or that's zero energy density states.
Thank you.
Thank you. Okay, that's a good question. Okay, so now I'm going to go over some very interesting construction that interesting to me, that I'm studying now, which is, the idea is obvious. There is only one case in this family which can work in 2+1 dimensions, which is m equals 1. Because m equals 1 is O1, and the group O1 is Z2. And Z2 can break even in 2+1 dimensions at finite temperature. So there is not going to be this infrared mechanism that leaves the Nambu-Goldstone boson. So, but of course, when you put m equals 1, you don't have these large n tools, at least not the standard large n tools. So you have to come up with something new. You have to come up with some idea of how to attack these models. So I'm going to tell you a little bit about how we've been able to do that. And this is directly in 2+1. I'm not going to talk about the epsilon expansions anymore, epsilon expansion anymore. So let me quickly review. So we're going to study m equals 1, but I'll start by just reviewing in half a slide some basic results about the ON fixed points. The ON fixed point in directly 2+1 dimensions, okay? So this is a way to write the Lagrangian of the ON fixed point in 2+1 dimensions. And at large n, where n is this n, we know the dimension of this energy operator, sigma, in some 1/n expansion. And probably several more orders are known, but it wasn't important for me to quote them. So what I needed to remember is that we have a fixed point in 2+1 dimensions where there is a primary operator, sigma, whose dimension is very close to 2. So if you put n equals 100, this is a tiny deviation, and it's like 1.99. So we have an operator of dimension very, very close to 2. So now, because we have an operator whose dimension is so close to 2, it's possible to couple it to other fields which have dimension 1, and it will be nearly marginal. So actually, that leads to a big class of fixed points that one can study that would be interesting to explore. So what's the simplest operator that has dimension 1? You just take a free scalar field psi that has nothing to do with the ON field theory. You add a new scalar field, and you couple the ON field theory to the scalar field in this fashion. This is a nearly marginal coupling. And in fact, you could generalize it in many ways. You could add Chern-Simons couplings. This idea of coupling something of dimension 1 to sigma is very general. You could do it in many other cases. But here I'm going to do the simplest case of coupling a real scalar field to sigma. So since this is a nearly marginal coupling, it's very tiny, it's very slightly relevant because the dimension of sigma is not 2, it's 1.99. So this is a very slightly relevant coupling. And you can understand the flows from this decoupled. So this is decoupled, and this introduces an interaction. And you can understand the energy flow completely because this is a very because the operator is very weakly marginal. It's just its dimension is 2.99. So you can use conformal perturbation theory to do that. And in conformal perturbation theory, it turns out that in this example, something really funny happens. You need to go to cubic order because all the terms up to cubic order are of the same order of magnitude. A, B, and C are order 1 numbers. And lambda is this coupling between the energy operator and some field of dimension 1, operator of dimension 1. So you need to go up to cubic order, and it turns out that the quartic and the higher powers are actually suppressed. Only the first 3 terms are of order 1 over n. Higher terms are of order 1 over n squared, 1 over n cubed, so you can throw them away. So it's a funny situation where the beta function is cubic, and you need 3 coefficients to make progress. In the model that I just told you, a funny accident happens, and that the coefficient b vanishes. So this vanishes. So the beta function has a linear piece and a cubic piece. And therefore, there are 2 fixed points. Well, there are 3 fixed points. One is trivial, where the 2 theories are decoupled. And then 2 fixed points corresponding to the 2 square roots. One of the 2 square roots is not surprising. It's just the ON plus 1 invariant fixed point. So you added 1 real field to the ON model, and clearly there is going to be a fixed point with an enhanced symmetry, ON plus 1. So that's one of the square roots. But the other square root is more interesting. It's a new fixed point. And it's directly the 2 plus 1 dimensional version of that fixed point that we saw in the epsilon expansion with m equals 1. So this is the fixed point. Here I wrote the Lagrangian. This is a fixed point, which is interacting and has this symmetry, Z2 times ON. So the first 2 terms are just the ON, familiar ON interactions. Then you have a kinetic term for the new free field psi. And then there is some coupling between the energy operator and psi squared. And you can compute the coefficient by solving this cubic beta function. So this gives a construction of a fixed point in a 1 over n expansion, an interesting fixed point. Now, this fixed point is quite interesting. It has curious thermal properties. If you ask what happens at finite temperature, it turns out the thermal mass for the field psi is negative. And I'm sure if Subir is here, he would recognize this immediately. That's all over his book, this golden ratio. So this is a funny example because it has a field psi with a negative mass squared, for the thermal mass squared for psi, and because it's negative, it leads to symmetry breaking. So this field theory that we're now studying is an excellent candidate to be the first example of symmetry breaking in an actual quantum magnet in 2 plus 1 dimensions, not a fractional dimensional field theory like the epsilon expansion ones. So this looks very promising, but we haven't proved yet that this is a fully unitary field theory. One has to do a little bit more work. So we found the beta function, we found the zeros, we have the fixed point, and we computed the thermal mass squared, and it's negative. So there is symmetry breaking, but to prove that this fixed point is unitary, one needs to do a little bit more, and that's what we're doing now. In particular, one has to prove that the potential is bounded from below. So that's what we're working on now. But it looks very promising, and it's the direct analog of what we saw in the epsilon expansion. Let me summarize. We learned that it's not impossible that the critical point would be in a broken phase at finite temperature. That means that if you embedded it in a phase diagram, a full-fledged phase diagram with some relevant operators, then the ordered phase would continue to infinite temperature, and the disordered phase would be capped off. I've given you constructions in 4 minus epsilon dimensions. I have not given you constructions in 3+1 dimensions. That's still an open question. Are there interesting weakly coupled gauge theories of the sort that Beng-Sachs constructed and Sentil recently studied, I think in some papers with Eugène B. Are there such of this sort? Are there theories of this sort that also have these properties? We do not know that yet. I do not know the answer. Those, of course, will be interesting because they can make better contact with black hole physics. For those of you that are familiar with ADS-CFT, let me just point out that such field theories they're basically vector models, and they do not have a full-fledged ADS-CFT dual of a standard sort. They are dual to something that's called Vasiliev theory, which doesn't have black holes, and certainly one should not have any intuition about whether or not they have a no-hair theorem. So it would be actually interesting to try to construct gauge theories because they might be a little bit closer to black hole physics. The Z2 times O(n) model looks an interesting model to study. It seems to have what we need in 2+1 dimensions. And I mean, there are lots of other questions about the number of relevant operators, the dimension of the phase diagram. One can try to see if there are any ways of simplifying this model and so on. But that's more or less all I wanted to say. So thank you so much. If there are any questions, I'm happy to discuss further.
Thank you, Zohar, for the wonderful lecture. Any questions, please? Audience.
Okay, I have a question. When you're like first investigating this, was there like, did you have any reason to think that the ON or like the biconical models would give something interesting, or is that like the first thing that you tried and it happened to work?
Well, originally, if you want, it's a question about history, right? So originally I wanted to prove no-hair theorem, and I spent a half a year trying to come up with a field theory proof that this cannot happen, that whatever I'm telling you here cannot happen, okay? And then I failed, and then we started looking at this epsilon expansion fixed points. Then we proved the no-go theorem for single Casimir models. And then we just looked at the first example that is not single Casimir. We started looking for numerical solutions of these beta functions, these ones. And we started saying numerically that some epsilon expansion fixed points seem to have negative thermal masses. And then, yeah. So we basically followed our nose, given that we couldn't prove a theorem. I should emphasize that in lattice models with finitely many degrees of freedom per site, of course, this is impossible because the high temperature limit of this density matrix, is 1 in lattice models. But in quantum field theory, 1 doesn't make sense. There is no such thing as the state 1 in quantum field theory. It only makes sense if you're in a lattice model with finitely many degrees of freedom per site. So really, if you're a condensed matter physicist, the way to think about what I'm talking about here is about symmetry breaking at scales which are much bigger than the lattice scale, but much, much smaller than the correlation length, okay? So in lattice systems, you have the correlation length, you have the lattice scale, and you can ask, can we say something about the temperatures at which the symmetries are restored? And of course, if you go to temperatures which are of the order of the lattice scale, everything will be restored because this density matrix approaches 1. But it's still interesting to ask about temperatures which are much, much higher than the inverse correlation lengths, but much, much smaller than the inverse lattice scale. And that's the regime where quantum field theory is a useful guide.
Can I ask a question?
Sure.
Yeah, so I'm wondering about how if you plot the temperature dependence of the entropy within the quantum field theory, so what does that look like?
Yeah, yeah. Since it's a conformal field theory, this is kind of trivial. It's t cubed, or t in 2 + 1 dimensions is going to be, it's fixed by dimensional analysis.
Yeah, no, I understand. But suppose I deviate slightly from the critical point and go into with a perturbed by relevant operator and go into the massive symmetry preserving phase, and then I come down in temperature. I think what you're saying is that you go from as you increase the temperature, you go from a disordered phase into an ordered phase. Right.
Correct.
So the ordered phase is higher entropy than the disordered phase in this case.
Yes.
Okay.
That seems bizarre, but I have no way of explaining it otherwise.
No, it's known to happen near some first order phase transitions, for instance, melting of helium or something. But yeah. Okay, thanks.
Mm-hmm.
I have a related question. So this behavior that your order parameter was actually increasing with temperature seems very similar to what happens sometimes in these models of non-restoration of electroweak symmetry. So you don't start with a conformal field theory again, but as you raise temperatures, people have built models where the electroweak symmetry actually doesn't get restored at high temperatures, but the wave of the Higgs keeps increasing with temperature. So is that a similar phenomenon as what you're finding, or you think that's a different?
Right. I looked at that literature, but all those constructions are, if you think about it in the in the context of cosmology, then it's fine. But if you think about it as in the context of quantum field theory, these are not statements about arbitrarily high temperatures. These are statements about some intermediate regime. So they're a little bit analogous to this thing that I told you about, this salt. I mean, they cannot be really, asymptotically true, because the standard model is not even UV complete.
Right.
These are statements about some intermediate phases of the electroweak symmetry. And of course, at very high temperatures, you would probably go back into a disordered phase where the electroweak symmetry is unbroken. That's comment number 1. And comment number 2 is that this is about the gauge symmetry. While here, I'm not talking about gauge symmetries. I'm talking about actual global symmetries, which have an order parameter.
Right. But I'm wondering if the comment about the entropy being larger, at least in this intermediate temperatures, the entropy in the ordered phase being larger or smaller, it would still apply.
Yeah, I don't know, but I think well, I have nothing to say about it. That would be illuminating.
Hi Zohar, could you just show the slide where you had your new model that broke the symmetry?
You mean the 2 + 1 dimensional model?
Yes. Is it which thermal the thermal mass was the next slide where you compute the thermal mass?
Yeah, so this is the model, okay? This is the model. It has Z2 times ON symmetry. I went quickly over it because it's not terribly the details are not terribly interesting, and you can the Z2 symmetry acts by flipping the sign of psi, and the ON symmetry acts by rotating the scalar fields phi.
Mm-hmm.
Okay. And then this is a fixed point. It's a given in an expansion 1/n. It's a fixed point that you can write down. It's very similar to the ON models, except that it has a negative sign here. In the ON model, the sign is plus. Okay, and then you can ask, what is the thermal mass of psi, and what is the thermal mass of phi?
Yeah.
So thermal mass of phi follows the same rules as in the ON model, because you basically took the ON model, you tacked another single degree of freedom, and it doesn't back react too much. So the thermal mass of phi stays the same as what it was. It's positive, and the phi's are at the origin.
Mm-hmm.
But psi behaves differently. The thermal mass of psi, which we computed, turns out to be dead. So the mass squared of psi is negative.
Thank you.
And so what happens at finite temperature is that phi develops a wave, breaking the Z2 symmetry spontaneously.
Yeah, psi develops.
Yeah,
right?
psi develops a wave breaking the Z2 symmetry spontaneously.
Thank you.
Zohar, can you say something about this intuitive idea that a field theory at infinite temperature looks like a field theory of one dimension lower? Does this hold up to this more careful scrutiny?
No, I mean, well, this is just for the Euclidean aspects of the theory, right? Not if you ask about dissipation and stuff like that. But here we're asking about the Euclidean. We're asking about the expectation values of order parameters, and expectation values of order parameters can be computed within the Euclidean prescription, which is that you take the field theory, you put it on a circle, and you get a theory in one dimensionless, which is local, unitary, and so on and so forth. But of course, it's not true for many other things you can ask about finite temperature, like viscosity and things like that cannot be captured in the Euclidean theory. You know what I mean? Or
Yeah, I agree.
the Euclidean theory allows you to compute the real parts of some Green's functions at zero frequency. But there are many dissipative properties which are captured by some imaginary parts, and they are not easily extractable from the Euclidean theory. But here I'm just computing one-point functions of order parameters at zero frequency. And those are, those are correctly reproduced by a path integral of the same field theory in a circle. The path integral of a field theory in a circle is not the same as the field theory in one dimension this, because even when the circle is very small, there could be effects that do not decouple. For instance, this mass. So for instance, if you took this model, which is just a mean field theory at long distances, and you reduced it on a circle naively, you would throw away all the Matsubara modes, right? You would just get that. And that is just a strongly coupled model in 2+1 dimensions. It flows to some kind of Ising fixed point, maybe, or maybe some massive phase of the Ising of the 2+1 dimensional Ising model. But it's actually incorrect because the limits do not commute. It's incorrect to throw away the Matsubara modes because what the Matsubara modes do is that they lead to a mass for this field phi to the zero mode. And this mass, as you can see, does not decouple when beta goes to zero. It actually blows up when beta goes to zero.
Right.
So the limit of a small circle does not commute with the limit of a finite circle and long distances. So the correct thing to do is to keep the circle finite and take the limit of long distances. That's a local field theory in 2+1 dimensions, but it's not the same as first taking the circle to zero and then taking the long distance limit. So I never do that actually. I always keep the circle finite and take the long distance limit. Okay?
Yeah, that makes sense. Thank you.
Follow-up question to the new model you had. You expect that the model you have generates a potential like a psi to the fourth potential that will bound the vacuum, yeah, keep a stable vacuum.
Psi to the 4 is a relevant operator. It's very much like psi squared. So by generate, you probably mean when you go on the moduli space. When
yeah, I'm just trying.
You're probably asking where is the vacuum. So I have a negative mass squared.
Yes.
And I want to know where is the vacuum. So what you need to do for that is that you need to excite psi, adjust the wave of epsilon and phi, and then find where is the true vacuum. We haven't done that yet, but studying the very same model in the epsilon expansion, we have found the vacuum. And there is a unique vacuum, and it's the potential is bounded, and so on. So we do not know. I do not know the answer to your question, but in the epsilon expansion, we already did this computation, and that's why I believe that the model is fine, because in the epsilon expansion, it had a unique vacuum. Everything is positive, no runaway.
I see. But you mean for epsilon less than 1?
Yeah, for a tiny epsilon.
Yeah, okay.
This is a family of filters that you can construct for any epsilon.
Mm-hmm.
In fact, there is a small miracle that maybe it's a good excuse to say. The dimension of the dimension of this sigma operator, as you know, is nearly 2 in any number of dimensions, not just in 2 plus 1. So it's always possible to couple sigma to something of dimension d minus 2. And psi squared always has dimension d minus 2 in any number of dimensions. So this is actually a weakly relevant perturbation in any number of dimensions. And you can study, and you can get, I mean, this formula continues to hold true in any number of dimensions. And then you can just take the limit of 4 minus epsilon space-time dimensions and make contact with the epsilon expansion. And everything glues very smoothly. And you find the unique vacuum. And now we're trying to extend that to to other dimensions.
I thought you were trying to say that my understanding was that your model will be at integer dimensions also an example where
Yes.
you have
Yes, what I'm saying is that strictly speaking in 2 plus 1, we have not yet found where the vacuum is.
Okay.
That's something that we're just working on now. But this model, this model can be defined in any number of space-time dimensions.
Yes.
And in 4 minus epsilon space-time dimensions, we already did find the answer of where the vacuum is. And it's perfectly healthy and there is nothing wrong about it. So I'm just giving you some, circumstantial evidence that the model will end up being a legit unitary field theory.
Yeah, that's what I'm getting at. I mean, is this going to be unitary or not?
I mean, if this example fails in 2 plus 1, I would start thinking again that there is some conspiracy, that maybe there is a theorem in the end of the day.
Yeah, indeed. Thank you.
Any other questions?
Can I ask a question?
Sure.
So let's go back to the phase diagram in the beginning.
Oh, you mean the one that I stole shamelessly from somebody?
Yeah. Okay. So so if we start with if we start with the 0 temperature transition and crank up the temperature, and if somehow there is a phase transition at the finite temperature T equals Tc, then does that mean that at 0 temperature, the critical theory cannot be described by a CFT?
Yeah, I think so, because the CFT should look the same at any temperature.
So it looks like it's an evidence that to exclude the second order phase transition at 0 temperature. Is that right? What I mean is that we can use.
I'm thinking about what you're saying. Yeah, I think definitely so. Because if at 0 temperature you have a first order phase transition, then already at 0 temperature you have a scale, which is the tension of the layer between the two phases. You might expect something interesting to happen at temperatures of that scale. So the first order line would go out. So if you had the first order transition at 0 temperature, what you might expect is that the first order line would just go vertically up and then disappear at some point. That's a that happens in many examples.
But so what I'm talking about is the second, the no-go for the second order transition.
Well, what I'm telling you is that if there's a first order transition at 0 temperature, then as you heat it up, it cannot disappear right away. If this is due to a symmetry. Suppose you have a broken symmetry at 0 temperature. So then there are 2 vacua which are degenerate. And if you heat it up, they cannot disappear. So the first order transition would continue to exist at some small temperatures, and then it will disappear.
But what I'm talking about is if we go up straight in the temperature axis, not moving along with the.
That's what I'm saying. If you just go up in temperature, the first order transition cannot disappear right away.
Okay.
Well, an evidence. So what I'm telling you is that what I'm saying is that you're basically right. If there is some interesting feature at non-zero temperature, that means that the 0 temperature theory must have been in the first order transition, not the second order.
Okay, thanks.
Yeah.
Zohar?
Yes.
So the related issue actually bothered me I hope there's still some superconductivity expert or Fermi liquid expert. So those like phase diagrams will be central. People they study. Usually there could be two older phases at zero temperature.
Yeah, like this.
Yeah, for example, and in this quantum critical region, at the high temperature could be some Fermi liquid, non-Fermi liquid, but the quantum critical point might be shed superconductivity dome. In that case, does that mean that the critical points that covered by the superconductivity dome cannot be described by CFT? For the reason that they are scales. One is the superconductivity above the dome, and also maybe Fermi liquid in the even higher temperature.
Well,
so they are some.
Strictly speaking, in this diagram, I don't think people know that it's a CFT. Many people actually think it's a first order transition in this diagram.
Right, but I'm saying one more thing, that suppose there is also another scale, set by lower temperature superconductivity, even before you heat up to a Fermi liquid, there could be a superconductivity instability.
Right.
Over that. So in that case, that the critical points, on one hand, it could be changed to, it could be first order, it could also be second order. And on the other hand, even if it's second order, it cannot be described by CFT, by your statement, or even the beginning of your assumption that the CFT can, at the non-zero temperature, can only have just one phase, right?
Well, if it's if it's a CFT obeying all the relativistic symmetries, then it has one scale, and it's the same at any temperature as any other.
Mm-hmm.
I don't understand what you mean. You have something in mind which is a CFT but has a scale? Maybe you're talking about some Lifshitz models. I don't know.
It could be. I'm saying the context what the condensed matter people talk about is critical points with one scale by superconductivity dome. There's a semi half circle around the QCP and also the Fermi liquid above the dome.
Right.
They cannot be described by CFT based on
CFT. That's right. That's not a CFT. That's not a CFT. Yeah. Yeah.
Thanks.
I mean, this kind of thing could be a CFT. This deconfined quantum critical point could be a CFT.
Yes, I agree. Yes.
Yeah, it could be, but maybe it's not always. Depends on the parameters. It depends on like the universality class.
Yeah. But the one on, for example, in the Coupe, that type of things was if there's a superconductivity dome, if there's a Fermi liquid or non-Fermi liquid or both, that cannot be a CFT, just based on there are two scales.
CFT, once you hit up a CFT, it's the same at any scale. So up to there is only one dimensional parameter, so nothing can depend on it. You just fix the scale once and for all. You just call this temperature 1, and that's it.
Thank you. Any more questions from the audience?
No.
Please feel free.
Yeah, well.
Can I just one last question? If you have more.
Yes.
Do you, so in all these examples, so in the example you had that you're still breaking a discrete symmetry, do you believe that there will be continuous symmetry breaking
in 2+1?
temperature?
Oh, you're talking about 3+1 or 2+1 dimensions?
Either.
Well, as I said, in 2+1 you can easily rule it out because it's the Kalman theorem. So the interesting question is: are there superfluid phases, like continuous symmetry breaking phases at finite temperature in 3+1 dimensions?
Mm-hmm.
And I have no idea. Of course, there is lots of places where you could look for it. You could look in weakly coupled conformal gauge theories, but I have no idea what's the answer. That's actually going to be much closer to ADS CFT, because the whole point of this ADS condensed matter literature was to look for superfluid liquid transitions. And so if there is a superfluid phase at finite temperature, that would, in conformal field theory, that would be a very violent violation of the no-Harry theorem.
Yeah.
So I have no idea, but of course it's would be nice to know.
Yeah, agreed. Thank you.
Thanks. Okay, no more questions.
Wait, I have another question.
Sure.
If you have something with a one-form symmetry, we discussed how they like to be broken at high temperatures. How is this reflected in the no-Harry theorem in ADS-CFT?
Oh, yes. So if there is a black hole, then it breaks a one-form symmetry, basically.
Explicit.
So in ADS-CFT, what you would say is that okay, let me just think for a second about how I want to say it. Give me a second. So in ADS-CFT, the dual statement of the statement that you expect higher form symmetry breaking at high temperatures is that at high temperatures there is a black hole in the bulk, and the reason is that Wilson lines in the presence of a black hole, Wilson lines in ADS-CFT are like stuck at the horizon, and you get the area law just from the Wilson lines moving along the horizon of the black hole. So in ADS-CFT, that's a very natural thing. You basically expect always higher form symmetry breaking at high temperatures, just by virtue of the fact that you expect black holes. So in fact, you could try to prove that in quantum field theory, right? So you could, instead of this statement that I wanted to study, you could ask the following question: take conformal field theory with a higher form symmetry. Is it true that this symmetry is broken at finite temperature? This is dual to the statement that there are black holes in ADS. Now, is it true? I don't know. I haven't studied that question, and it may or may not be true.
That's very interesting. I didn't understand why you say that the Wilson lines on the horizon have area law.
Well, that's something that they've shown in, when they came up with the ADS-CFT correspondence. It's a classic result that when there is a black hole, Wilson lines have an area law. It's a computation of minimal surfaces. Basically, once you have a black hole, the minimal surfaces look like rectangles, where the base of the rectangle is on the horizon. And it's a classic, it must be in Juan's original paper on Wilson lines in ADS-CFT, or Ed's. It's some classic result in ADS-CFT from 20 years ago.
Cool, I'll try to look for it.
What did I say? I must have said it exactly the opposite of what I should have said. Did they say the opposite?
Well, you said they have area law, but we want the one-form symmetry.
Sorry, I meant the opposite, of course, because it's a rectangle that's moving on the black hole. You get a contribution from the length of the strip on the black hole, so it's perimeter. It's the opposite of what I said. I'm sorry, I said it completely oppositely. You get a rectangle where the base of the rectangle is stuck on the horizon, and the expectation of the Wilson line, expectation value of the Wilson line is just the length that is of the strip of the Wilson line that is moving that is stuck on the horizon.
Right, so, like you can imagine there are field lines with tension, but they can just go into the horizon.
Exactly. So you take field line with tension, they drop in the bulk to the horizon, and you get a contribution from the length of that strip.
Okay, cool.
And that's the deconfined phase in ADS-CFT. So the black holes always lead to a deconfined phase. So you could try to prove that statement. Now, is it true? I don't know. But it would be nice to know.
Sorry, the global symmetry context in the CFT side will be translated to the higher form or just ordinary gauge symmetry in the bulk and the black hole side, right? So all the context you just mentioned should be gauged.
I'm just talking about the ZN. Take a gauge theory that has a ZN one-form symmetry. Very easy, like take SUN times SUN with some adjoint matter, with some bifundamental matter. So you have ZN one-form symmetry. Put the system at finite temperature. Does it break the ZN? All right, that's the question. Does it break the ZN one-form symmetry? I mean,
but I say on the black hole side issue related to ZN1 from gauge symmetry or something like that?
Yes. In ADS-CFT, the ZN global symmetry of the boundary in ADS-CFT, this translates to a ZN two-form gauge field, which is either Ramond or the Neves-Schwarz, the NSNS two-form gauge field in the bulk. Actually, there was a recent paper about it, which was very illuminating, explaining how which gauge fields in string theory lead to these two-form gauge fields in the bulk. And I forgot the authors, but it was, And so the question turns into a question about whether those two-form gauge fields are Higgsed or not.
Okay, I think it's about the time. So if there's any last question, I think you have 30 seconds you can ask. Otherwise, I think there will be additional noon seminar soon. So any more questions last time?
Okay, thanks so much.
Yeah, if not, thanks Zohar. Thank you very much.
Thank you so much. Have a
Thank you.
nice day.
Zohar.